So I'm Muhamed Amin. I just moved from the University of Groningen to the NIH. I'm working mainly on using machine learning and DFT calculations and electrostatics to predict oxidation states, and I also do simulations for single particle imaging at the Center for Free Electron Laser and DAISY. Okay, so today I will talk about a system that it's a really complex photosystem too, and I will talk about different techniques that used to image the chemical reaction, which is X-ray and X-fill and cryo-EM, and how we can use machine learning to predict the oxidation states of the metals in the complex. Okay, so metalloenzymes, we all know that they are just proteins that include metal centers in their active site. And oxidation of states of these metals are essential for the chemical reaction. The problem when you image such systems is that you generate a lot of electrons and they just mess up the oxidation state of the metal. New techniques like X-fill overcome radiation damage by shooting a very short pulse on a femtosecond time scale so that you can get a diffraction before destruction. So hopefully you get the structure without damage. But the problem is that they also have other level of experimental challenges that because you destroy crystals, you really have to get diffraction patterns from identical crystals in the same chemical conditions, which is not trivial. One system is really sensitive to this kind of imaging techniques is the oxygen evolving complex of photosystem 2. So the complex in its core has 4 manganese centers, and these manganese centers are oxidized in a catalytic cycle called the Cook cycle. So each time the primary donor, it's a chlorophyll molecule that absorbs a photon, and then this photon absorption induces an electron transfer that start from the oxygen evolving complex that pulls the electrons from water, and then after 4 flashes or 4 photons, you get to release 2 hydrogens and oxygen molecule and 4 electrons. 4 hydrogen, 4 electrons, and oxygen molecule. Okay, and then, as I mentioned before, the X-ray before the X-fill, when you image the system with X-ray, you reduce the manganese, and we knew that it's reduced structures because we can look at the distances between the manganese and the ligands. We know that these are not high valent manganese. In 2010 or 2011, this experiment is called diffraction before destruction, where you really have identical crystals through an injection system, and then you did get a diffraction pattern from each crystal, and then you can, because the problem is that you cannot rotate it anymore because you destroy the crystal. So you really have to have an identical crystals and maybe a few thousands to resolve the structure. So you can cover all the orientation in something called Monte Carlo integration. Well, the problem here that it's unlikely that you have identical crystals that you really solve the exact structure for all of them. So for example, you will never have 100% of the same chemical state. So if you have 60 and 40, then you will not also image the required chemical state. The problem is that this kind of structures, people used to publish them saying, okay, this is the S2 and this is the S3, but how would you evaluate them if you are not sure about the population of the crystals you have? Well, we have like 30 structures in the protein data. Even from the same group, when they image the same chemical state, you could find disagreement with their structures. When I say disagreements, maybe it means like you will see for one metal, it looks like manganese 3 because we know that the distances are longer than manganese 4. We also see Ian-Teller distortion, but for the same group with a different structure, you see something different. So how would we evaluate this? Well, how we know the chemical state? We can know the chemical state by knowing the oxidation state of the metal, right? So if we know the oxidation state, we can decide which chemical state. But how we know the oxidation states? So there are different ways to do this. But the approach we took is just to collect a huge data set of small compounds of manganese, where we know the oxidation states beforehand. And then we build a machine learning model to do the prediction. So we started with Cambridge database. We collected a few thousand structures, and then after the refinement, in total we had like 3,000 structures. But I just want to mention that for these small compounds, we have published before that electrostatic dominates the interactions between the manganese and the ligand. So it's very obvious and it's very easy to see that if the ligands have within a distance from a manganese, then you know that this is manganese 4. For example, oxygen to manganese, if it's oxygen mu oxybridge and the manganese is 4, we talking about a range of 1.8 to 1.9 angstrom. If it's 2.1 or more, for sure that this is manganese, not manganese 4. We previously calculated the EM reduction potential and pK of the ligands using continuum electrostatic. We had to tweak the model a bit, but at the end, we got a very good agreement based only on electrostatic. No quantum effects are included, except that we get structures from quantum mechanics. Okay, so how it works? Well, we need to we have a big data set. Okay, and from this big data set, we can build a machine learning model based on some features. The features here are it's obvious, the ligand to metal distances. And then with this model, we can classify the structures to manganese 4, 3, and 2, and then we go to the protein afterwards. But we have to evaluate the model on small compounds first. So at the end, we don't have much. I mean, we started with 15K, but after pre-processing and clearing the data, because the data include manganese with ligands that are not with atom type that are not in the photosystem too. For example, you could have a sulfur ligand or other types, but you cannot use these to predict structures where the ligands only oxygen and nitrogen. So we removed all the ligands except if all the compounds, if the ligands are not oxygen or nitrogen. At the end, we left up with around 2,500 structures. Okay, and what are the features? So initially, I started with having 12 features. So you have, talking about octahedral manganese, so you have 6 ligands and 6 ligand type, 6 distances. And I actually ran the model and the prediction wasn't really different. We're actually the same if I only use 2 features, which are the average distances between the ligands on the equatorial and the actual the equatorial plane or the axial ligands. So meaning I take this 4 and average them. You see here this 4 water bound to this manganese. I take these 4 distances and average them, and then I take the actual distances and average them. And the reason for separating them for equatorial and axial, that you can detect something like the Ian-Teller distortion, where you see elongation of the bond length on one of the axes. Okay, so if you plot this for all these compounds, you will see something like this. So you see in the top figure, so this is the axial versus equatorial distances, and you see so the labels are based on the experimental labels. You see some of the manganese 4, and then here it's manganese 3, where you see on one side it's longer than the other side, which is that's the Yantalar distortion, and then you have the manganese 2 again with this effect is different, and you see that these 3 clusters are really well. I mean, you can know what the type of the oxidation state, what is the oxidation state of the metal by knowing the distances. You see here some distribution that didn't really make sense. So I used k-mean clustering to I provide the data to unsupervised learning algorithm, which is k-mean clustering, saying, okay, please cluster these to 3 clusters, and then you get this clean kind of cluster at the end, where you correct for some experimental problems where you don't assign the experimental oxidation state correctly. And then I use this clean data to do a prediction using decision tree classifier and naive Gauss base as well. And at the end, I get this confusion matrix. Confusion matrix, if you know it, it's just a matrix that tells you the predicted versus the actual oxidation state. So, for example, if you see here on the top left, this is before clustering, and this is using a naive-based classifier. So the diagonal elements are the elements where you predicted correctly. Any off-diagonal element is something that you didn't predict correctly. For example, let's say here, you predicted as manganese 3, but it actually was manganese 4. Okay, so the accuracy score is pretty high, which is after clustering and for decision trees was we got to 100% accuracy. And even before clustering, it was like 97 or 96 accuracy. So the accuracy score was really high for this classifier. So yeah, and then the problem came here that, I mean, when I sent this when it was sent to the reviewers, the accuracy score for the small compounds is really high, but then when we did it on the exfil, we almost didn't match except any of the third structure except 1 or 2. So especially for the higher S states, for the dark S state we did well, but for the higher S state we didn't match with the exfil prediction. The problem that reviewers were arguing that it's not really a good model for proteins. Small compounds are not a good model for proteins. But the thing is, the manganese chemistry shouldn't change much going from small compounds to proteins. So if we did all the structures in the exfil, we did the prediction for these structure, and as you see here, even the 2 monomers are different. So and they are also different from the experiment. So in the experiment, you see it's more oxidized than what we get in the machine learning prediction. And then the next step was really how to validate this. Well, we had to come up with another method to do the validation. If people arguing that small compounds are not a good model, then we have to prove somehow that they are a good model. The other method we used is the valence bond method. So it's just an empirical method for calculating oxidation states, also based on the metal ligand distances, and based on some empirical parameters that already fitted in a database previously. And when we did this, we see a good agreement with machine learning prediction and the valence bond calculations, as you see here. So we have also we added another way of validation is DFT. So we take the active site, we put it to DFT, and then we do a single point calculations. We get a wave function. From this wave function, you can calculate spin density on each atom center. From this spin density, you can predict the oxidation. So you can calculate the oxidation states. For example, here, in this HO, which is assigned to be S3, we calculated for manganese 1 to be to have a spin density of 3.1, which is manganese 4, right? Because manganese 4 has 3 electrons in the d orbitals, so that's why it's manganese 4. So, and if it's higher, like if it's 4, then it's manganese 3. If it's 5 spin density, then it's manganese 2. And we also went a step further by optimize the structure with DFT and then compare with the prediction of the machine learning. We really had 100% agreement with optimized structure. So if I take a protein and I take the active side, optimize with DFT, and then take this DFT structure, make prediction using the machine learning model we built on small compounds, then at this case we get 100% accuracy. So it means that there is really something wrong with the exfil structures. Maybe the resolution, I'm not really sure, but there are several experimental challenges in this kind of structures. Okay, and also we went to we tried some other proteins where the radiation dose wasn't that high, and also the resolution was pretty high, and the machine learning model did very well with this. Okay, and the second part here that I will just go through quickly is if you already have, so in one of the structures, one of the S states, S3, we have several models for this structure, even from DFT. So how would we know that these structures are how to evaluate these structures? Not now about evaluating the oxidation states, but evaluating how reactive are the structures. If we expect a certain chemical activity, how would we evaluate that this structure is valid or not? So an underestimated DFT methodology that is not being used a lot these days is called Conceptual DFT, where you use quantum descriptors to study the reactivity of your compounds. So for the S3, there are several models. You have a model where an oxygen inserted to be an extra ligand to manganese 1. You have another model where you have the oxygen inserted to be an extra ligand for manganese 4. And you have another model where no oxygen inserted at all, and you form a radical anion in W1. So what we do here is try to evaluate, because this is the state where that precedes the formation of O2 bond at the end of the catalytic cycle. So we expect some reactivity. We expect that the oxygen to be reactive. So how to evaluate the reactivity of this oxygen? So it's basically we use something called quantum descriptors, which is I can define it here. Is the derivative of the electron density with respect to the number of electrons. So if you would add an electron or remove an electron, how the electron density would be affected. And from there we can decide the electrophilicity and nucleophilicity of the oxygens. And we see here that the oxygen evolving complex have this very special structure because it actually could make this oxygen on the cube nucleophiles and the oxygen on the terminals electrophils. So we can know that now this would reduce the barrier to make O2. So the problem is that you still see that these structures are not really reactive. Only here you see that O4 is really reactive. So this is in this curve, what you see here in the bar graph is something called dual descriptor. It's the quantum descriptor that is a measure for nucleophilicity and electrophilicity. So red is nucleophilic oxygens, and blue is electrophils. Okay, so you see here that the oxygens on the terminal is electrophil, and the oxygens on the cube are nucleophil. You see here. And if you change one, if you move this O5, for example, to bind manganese 1, and we move to O6 to bind manganese 4, you see the switching here. So the labels are not exactly the same on the y-axis and the x-axis. So you see a switch from being electrophil to a nucleophil, which is maybe this is why this unique structure of the OEC make it lower the barrier for the O bond formation. So, but also we compared the S3 against the stable S1 structures, and here we didn't see much difference. So, meaning that this structure is very stable, thermodynamically stable, and then this means that you need to do another structural changes before forming the O2 at the end. And also compared against a model compound, when we know that there is no bond, auto bond formation in this model compound, and that the dual descriptor value is very close to what we get in the S3, except for this structure where you have a high activity in O4. So O4 is pretty reactive here. All the structure that was proposed to have a radical anion in W1, of course, you see it very clear here that it's very nucleophile. You remove the proton from all the proton from W1. That's why you see it's very reactive. So at the end, this was the conclusion that the OEC is reducing the barrier to form O2 by forming a nucleophile and electrophile oxygen next to each other. And we also see that the nucleoxide bridges are more reactive than the terminal water. And we need to do more structural changes in order to do the bond formation for the current proposed models. Yeah, and that's it for today.
Thank you. Thank you very much. Are there any questions in the audience? Yana Shen.
Nice talk.
Thank you.
So the Fukui functions you use, right? So it's one way, but we and others found that the omega, so the electrophilicity index, is actually a better measure for a lot of systems. So you could perhaps try that.
So yeah, I actually also thought about using the contribution in the HOMO as well, in the contribution of each atom in the HOMO orbitals, and it's kind of gave me a very similar results to what I get from the Fouquet function, but it's a good idea. I will also try it. Thank you very much.